cloud. So the first problem here on this new page, whatever I said, page 4, is find the area of the rectangle. And it's almost exactly the same in terms of structure as the one that we did last class, but it's good to have a second look at this, right? And so what we want to do is we want to use our knowledge of triangles to get the job done, right? So our knowledge of triangles just boils down to this idea that the area of a triangle, oops, got to turn the pen on. Is half the base times the height, right? And so what we're looking at here again, kind of rehashing some of the stuff we talked about, but I'm looking at two congruent triangles. So what that means is that the area of the rectangle is going to be two of the areas of the triangles. And if the area of a triangle is half the base times the height, and we want two of those, 2 times a half, so the product of the 2 and the product of the half would be equal to 1, you'd get a result of just base times height. All right. So if we have a base and we have a height, then we have what we need. All right. So I have a height. Let me use a highlighter for that. I just need the base. Right now, opposite sides in a rectangle are congruent, which is one of the reasons why we talked about those properties. This side is congruent to this side. So if I figure out one, I've got both. Right. This side here is congruent to this side. So again, if I have one, I have both. So I know that this has to have a dimension of 3 or a length of 3. And we also know that regardless of the orientation of the rectangle, they said it's a rectangle, so we know all the properties of rectangles are in play here. We know that there's got to be a right angle, right? So I'm going to use a squared plus b squared is equal to c squared. And the only thing you got to be careful about, it happens all the time in math. We're using b for one thing down here, and we're using it for something else up here. These are two different b's. This is b as it applies to the Pythagorean theorem. This is b as it applies to the half the base times the height, or in this case, base times height formula. Right. So you just got to keep that in mind. It's not the same b, or not necessarily the same. Right. So I'm looking for this side here, which I could call b if I want, but I'm going to call it a. So a squared plus 3 squared is equal to 10 squared. So a squared plus 9 is equal to 100. And a would be, or a squared. If I subtract the 9 from both sides, it's going to be equal to 91. And so just quick subtraction. Sorry, I feel a sneeze coming on. Lost it. I was going to do the quick mute, sneeze, and then unmute deal, but not that it would have been too crazy to sneeze on a live Zoom. It's just my sneezes are like abrupt and scary. So if you're not ready for it, you might have gotten a little alarmed. Let's put it that way. So anyway, take the square root of both sides to get the a alone, and you get a is equal to the square root of 91. All right. So it's a squared plus 3 squared is equal to 10 squared. So a squared plus 9 is equal to 100. Knock the 9 off of both sides. That gave you a 91. And now we have the square root of 91, which if we can break down, we should. But, look for factors of 91. 91, oops. 91 divided by your popular perfect square values. Well, 1 wouldn't help, but 4, no. 9, no. 16, no. 25, oops. 25, no. 36, No, and then once you get more than halfway to the 91, you stop trying because it's not going to be a product of the perfect square. So it might be factorable, but its factors won't involve a perfect square. All right, so radical 91 is where we would leave that, but now that's the base. So the 3 would be the height. So in my area of a rectangle formula, base times height would be radical 91 times 3, or we would just write that as 3 radical 91. And it would be square units, but it didn't give us any units here, so I'm not going to lose any sleep over putting the units down or not putting units down. But technically, if you wanted to include the units, it would be unit squared. So you're not really saying too much of anything except for knowledge that they are square units. It's more like academic than practical. If I can get this fit, of course I can do that. All right. So that was the case of the rectangle. In the case of the trapezoid, I got the labeling right for a change. Again, we're using our knowledge of triangle areas. So what I would be looking for is this triangle, if I can get a right angle, this triangle plus the rectangle in the middle, plus the other triangle. Trying to sync up my speaking with my writing. Not quite, but I guess I'm going to leave it. All right, so I'm just going to put the little right angle marking there, make it apparent, or I'm going to say obvious. It's not always obvious, but it's acknowledged that it's a right angle, regardless of the quality of the diagram. It's a little box. All right. So this whole distance here, I'll zoom back out in a sec for those still looking at the previous example. All right. This whole distance here is 9.8. All right, that whole shebang. So from here to here, we have 4.5. Now, in a trapezoid, opposite sides are parallel. In an isosceles trapezoid, the legs are congruent to one another. So this side has the same length as this side, right? But what happens is when we drop an altitude, so when we drop a perpendicular here and here, we're creating two parallel lines. This is going to be parallel to this. We already know that these two are parallel. I'll just put one arrow there. So what we just created was a parallelogram, right? Parallelograms. Oh, hold on, I'm sorry. I leaned back and now I'm going to hit it. Right. So in a parallelogram, the opposite sides not only are parallel, but they're congruent, right? Add to that we now have a right angle. This inner figure is going to be a rectangle. All right. So everything that goes with being a rectangle is in play. Right. So opposite sides are congruent and all that good stuff. Right. But we knew that from being a parallelogram anyway. The rectangle part of it's going to allow us to apply the Pythagorean theorem. Right. So I know now that this side here has to have a length of 4.5. Right. If I do a quick 9.8 minus 4.5, we get 5.3. 5.3 split among the two fringes there would give us two little line segments here. Now the numbers aren't going to be pretty, so we're not going to expect our answer to be in simplest radical form. But this would have a value of 2.65, and this would have a value of 2.65. All right, so we have those dimensions. All right, but we don't know this side here. And that's what we would need to know in order to figure out the area of this trapezoid. Right? So if I take the area of that first triangle, area of a triangle, again, half the base times the height, and I multiply it by 2, so 2 of those area of triangles, I'll get 2 times half the base times the height, which is going to be base times height, right? But just bear in mind that the base I'm referring to would be this base. And the height that I'm referring to would be whatever this height is, right? Because if I take this triangle here and remove it and flip it around, I would create a rectangle over on this side, all right? So I'd end up with a rectangle multiplied, or I'm sorry, a rectangle area added to another rectangle. Right? So that looks pretty messy, so I'm not going to leave that in there, right? So long story short, I have to figure out what the length of this side is here in order to make this whole thing work, right? So I think I did the same thing I did last class, and that is I left off one dimension. I wish I could make it through a handout without making a typo. So let's say we know that this leg here is, it really doesn't matter, but I'm going to make it 3. Right? So this is the typo that should be there. All right? So if this is a 3, we have the ability to figure out what that height is, right? That pink highlight. Right? So a squared plus b squared is equal to c squared. I'm working off just this triangle here. All right. So the base, we'll call that a, so 2.65 squared. The height is unknown, so we'll leave that as b squared is equal to 3 squared. And we'll just crunch the numbers there. 2.65 squared isn't something that we would do by hand. So I'll just pop that in. I mean, you can convert it over to fraction if you want, but that's not a very good looking fraction. So we'll just leave it as a decimal. So 7.0225 plus b squared is equal to 9. I think I mentioned this last class, but there is a way to figure out that area, but you'd have to use trigonometry or more complicated algebra. So it's just easier for me to just make up a number. That's why I put 3 there. And that's why I keep forgetting to put a 3 there, because I know that you can do it another way, and I keep losing track of that. Right, so I'm going to take that number away from 9. I'll just tuck in a 9 minus in front of it. So b squared is equal to 1.9775. And then I would need the square root of both sides to get the value of b. So I'll just retype 1.9775. And then we got this disgusting decimal here, but it's irrational, so it kind of makes sense that it would be disgusting. All right, so, but it's not our final answer, so I'm going to hang on to this whole decimal. So 1.406236111104. All right, so now that's the measure of this height here. Right, so we now have enough information to figure out the area of this trapezoid. So I'm going to take the base of 2.65. Right, so I'll work on the 2 triangles first. I'm going to take the base of 2.65 and multiply it by the height that we just came up with, 1.406, blah, blah, blah. Then I'm going to add to that the area of the inner rectangle. Which has dimensions of 4.5 multiplied by that height. So essentially, I'm taking this and adding to it this. And that's going to give me my entire area. All right. So it's like, okay, well, that's a lot to type in. But what you can do is you can set whatever this value is. I have it in Desmos here. I can set it equal to whatever I want. Since that's the height, I'll just say h equals. And now anytime I type in an h, it's going to bring back that lengthy decimal. So I can do 2.65 h plus 4.5 also h. Right? And so the total area of this trapezoid would be that lengthy decimal. And you know, if you're not given any rounding instructions, your best bet is to just put the entire decimal down as your final answer. Now, there are shortcut rules for all this stuff. The issue is they usually involve more than just simple algebra. Simple algebra is not wrong, but simple geometry. And we want to keep it to simple. We don't want to get into the world of trigonometry, right? So yeah, that's just something to keep in mind. But if you recognize the little relationships, you can save yourself a little bit of time anyway. You know, like in the case of the rectangle, base times height. You know, it's like you're taking the two triangles, adding them together, and you're getting the total area. But it just turns out that that's the area of the corresponding rectangle. Same thing happens with the parallelogram. And I've tried repeatedly to draw this correctly, and I'm never successful. I'm going to try it one more time. So if you take this triangle and move it on over here, you never get it to quite fit. But this rectangle here is going to have the same area as the parallelogram. Okay? There's something called Cavalry's principle that we're going to get to in a little bit. But basically, it's saying that if you have two geometric figures, in 2 dimensions anyway, if you have two geometric figures that have the same height, the same width at every height, then they're going to have the same area, right? So if I take a rectangle, so I'm going to take this line segment and make it correspond to a rectangle. And I'll just steal this here. This rectangle that I'm producing is going to have the exact same area as that original parallelogram. And the way I know is because their heights are identical. This height is the same as this, right? And their lengths, the widths at every height are exactly the same. So if I take this length or width, or depending on how your perspective, and bring it up through the rectangle, it's always going to be the width of that rectangle. Right? It never deviates from that. It's always the same. Right? Now, but the same is true for the parallelogram, I just have to travel along the diagonal movement, but it always represents the width of the parallelogram, right? So they both have the same height and they both have the same width. So why wouldn't they both have the same area? Right? So that's a little bit of the theory without getting into a formal proof. The bottom line is I can do all the crazy work that I did up here, or I can say, well, if the height is 4.5 and the width is 8.2, and these two figures are going to have the same area, then I would just figure out the area of the corresponding rectangle rather than worrying about the parallelogram itself. So the area of a parallelogram is base times height. It's the same base and the same height as that of a rectangle, the corresponding rectangle. So in this case, 8.2 multiplied by 4.5. So I just need to crunch those numbers, and I have it. So 36.9. And again, the units, oh, it froze, lovely. I'm sure it'll come up in a second, but the units are gonna be square units. It's just a question of like, okay, are we talking meters? We're talking about inches, yards, whatever. These were not given in terms of units, so you could either put in units squared or you could just leave it unitless, at least for any assessment from me. You know, like you go walking into another class down the line, and I'm sure somebody's going to be very particular about that sort of thing. You know, every teacher's got their own peculiarities. Mine kind of change from year to year. It's I'm consistently inconsistent, I think is the statement du jour. So anyway, so we're going to apply this information to three-dimensional figures, which is, I think, or it should be interesting, you know. Interesting being the first word of the day. Interesting. And there's a slight chance I used that word already, but that doesn't matter. That's fine. Okay. So the interesting, as in what I'm about to teach you, is the first word of the day. So to find the volume of a three-dimensional object with uniform cross sections, right? So that's something that we're going to have to wrap our brains around, right? Uniform cross sections. We multiply the area of the base of the object by its height. That last little bit, that's the easy part. Knowing when this concept applies, that's what's challenging. We multiply the area of the base of the object by its height. So if you could figure out the area of the base of the object and you know its height, then you can figure out the volume. But it would have to be an object with uniform cross sections. And it's like, okay, well, how do we know that? Right. So for that, I'm going to take us over to GeoGebra. I think I'm going to do it on the computer to let me pause the resume recording. So this is a three-dimensional coordinate axis or system of coordinate axes or set of coordinate axes. I like to turn off the plane just to make it look a little nicer. But when you look at a three-dimensional I just lost the term. Environment. That's not the term I was looking for, but that's the one I'm going to live with. What you're looking at is three physical dimensions, length, width, and height. Right. So I'm going to turn on the x-axis labels. Same thing for y. So you can see which one is the length, which one is the width. The height should be obvious, but I'll turn on that label also. Okay, did I not turn it on? I must not. I turned it on. I don't know why it's not. All right. Well, anyway, the red is the X, the green is the Y, and the blue is the Z, right? So length, width, and height. So what I'm going to do here, and I'm not going to ask you to do this part, but I'll just show you really quickly what I mean by an object with uniform cross sections. Right. So I'm going to produce a cylinder here. Right. So let's say x squared. You don't. Again, you don't. I'm just thinking out loud here. Plus y squared equals let's say 4. All right. So that's a cylinder. It's an infinite cylinder, which means it goes up and it goes down forever, but it's still a cylinder. If I look down from the top, you can see it's circular. Right. The top-down view is really a good view of a cross section. It would be the topmost part if it were a filled-in cylinder, but it's not. So, but what I can do is I can create a plane. I'll call it z equals 0. Right. So what's happening is I'm taking a plane and slicing through my three-dimensional figure. Right. Where it slices through, see that little area where it cuts? That would be a cross section if we were to lop the top off. All right. But if I go up or down, you'll see that no matter where I go, the size of that intersection never changes. All right. So this little, it looks like an oval, but it's really a circle because from the top down, you change your perspective, it's circular. But from the side view, just to get a perspective going, it looks like an ellipse. It looks oval, right? But no matter where I go, the size of that figure is never changing. All right. So let me see if I can do the intersection to make it pop. They changed the functionality a little bit here, but plane quadric 0, so P and EQ1. Yeah, there we go. All right. I do remember some things apparently. So yeah, that blue dashed curve would be the boundaries of the cross section. Right. So anything in between would be the cross section itself, and you'll see that it's not changing no matter where I go, going up or going down. Its width is never changing. Right. It may seem like it is because of the perspective, but it never is. Right. So that's the idea. Right. Now, it might not necessarily just be a cylinder. It could be any figure that you can think of that would have uniform cross sections. But sometimes, at first glance, it looks like, oh, maybe it won't, but it does. Sometimes you have to rotate the figure, look at it from a different perspective. But the ones that we work with will have uniform cross sections. Right. So let me. So now we're looking for volumes of solids with irregular bases. Okay, so it's kind of the rationale behind the methodology on volumes with regular bases is that you can use that information to kind of translate it over to this concept. Right. So first off, we'll start with the area of a polygon, of unknown configuration. But I mean, it's part parallelogram, part triangular component, but it's not the easiest thing to work with if you wanted to break it up into triangles. But what you can do, one technique is it's a rectangular approach. I'm not sure what the name is. I probably should know this, but it's never been an issue. Just encase it in a rectangle. Right? So you encase the entire figure in a rectangle. and subtract off the parts that you don't want. So you'd find the area of the overall rectangle and say, all right, well, there are pieces here that I don't want. And it'd be like, well, what are the pieces that I don't want? Well, I don't want this piece, I don't want this piece, and I don't want this piece. So we'd get rid of those. Let me get rid of the highlight. But what I do want is the figure in the middle. So I want all this. I can never make it. I do my best. Well, anyway, so this is what I'm looking for. This other stuff here, this and this and this, I don't want to do that. Right? So I have this on a set of coordinate axes. So it should be pretty easy to just count boxes to figure out what each dimension is, because each little cluster of points is worth 1 unit. And so since it's a rectangle, the distance, opposite sides are parallel, the distance from side to side will be consistent. It'll be the same from, any point along this figure, right? So we have 1, 2, 3, 4, 5 units along the outer dimension. So that's from top to bottom. And then from left to right, same deal, let's count boxes, quote unquote boxes, from beginning to end. So 1, 2, 3, 4, 5, 6, 7. So that would be a total of 7 units. So this would be what we call an overestimate. The area of the rectangle. We'll call it a rectangle. The area of the rectangle would be 5 times 7. That's going to be way more than I would need in terms of total area. 35 square units. Right? Now, if you're thinking about how much money you need to go out to dinner, and it's like, this is all the cash I have. Let's see. Well, the burger is going to cost $12. Well, let's say 15. A drink's going to cost $7. Let's call that 10. And maybe an appetizer will cost like $5. Let's call that another 10. You're 15, 10, and 10. You're at $35. That's more money than you need, maybe, but you're not taking any chances. Right? But if you're accounting for material, you want to have exactly what you need. Otherwise, you're going to have a problem with it. Right? So, because you just think about, how many people do any kind of woodworking or anything like that, but if you want to have roundabout what you need in order to do the job, because you've got to transport the materials, and that costs it's time, effort, and money. Right? So what I need to do is try to get a little bit more precise. So what I'll do is I'll first lop off this triangle here. All right, that has dimensions. We know it's 5 on one side, 1 unit on the other. So this triangle, area of this first triangle, I'm using color coding, so it should be all right. Half the base times the height. You can call either the 5 or the 1 the base, it doesn't matter. 1/2 of 5 times 1. It's going to be 5/2, or you could say 2.5. All right. So then let me grab another color and let's lop off this triangle here. This triangle has dimensions of 2 by 1, 2, 3 units, 2 by 3. Now, coincidentally, it doesn't always play out this way, but this other triangle also has dimensions of 2 by 3. 1, 2, 3. 1, 2. So they're congruent triangles. How do I know they're congruent triangles? Well, side angle side, because these are both right angles. Congruent triangles have the same area. Right? So I would figure out the area of the triangle, 1/2 the base times the height, again, 1/2 of 2 by 3. That's going to give me a result of 3, but 2 of those triangles, 2 times 3 would give me 6. All right. So in all, what I got to do is I got to count for the 35 units that I have in total. I got to knock off the 5/2, and I got to knock off the 6. Right. So you might be better off working with 2.5 as opposed to 5/2. Either way, 35 minus, you do it in either order. 35 minus 6 is 29, minus 2.5 is going to be 26.5 units squared. Right. Again, 35 minus 5/2 minus 6, 26.5. Right. So you can do it that way. So manually or in your head, not manual, well, manually, depending on what you define manually as, or in your head. The one thing you shouldn't really have to worry about doing is getting a common denominator and things like that. That's not really necessary. Okay. Now, we have this funky looking prism here, which I created on GeoGebra. Surprise, surprise. I don't think I saved it. All right, let me take a quick look. Might have. Sometimes I save. Just don't ever remember what account I use for this stuff. Yeah, I did actually, shockingly. 1 second here. Oh, well. All right, it always gets either too cold or too warm in here. All right. So let me pause the recording. All right, so when we're looking for the volume of this prism, we're really first looking for this base area here. I have to figure out what this base area is. And then I'd have to investigate to make sure that that is a consistent cross section throughout the entire figure, so that I could just multiply it by its height. And it appears to be. It's traveling throughout the distance. So for irregular figures, it can be a little trickier to verify these things, but it does appear that if I could figure out the area of this figure, that I'll know the main component of the body. Right. And so we take it back to what we just did. You look at this figure and compare it to that one, it's got the same configuration. Right. Now, if you look a little closer by the coordinates, this one has a coordinate value of -4. You go over to the left 4 and down 3. This one also has a coordinate value if I go to the left 4 and down 3. So this coordinate value here at B is -4, -3. Right? It's exactly the same. It's just it's scaled a little differently. And if you go to all the other coordinate values, you'll see it's exactly the same. Right? So this here represents the base area of this figure there. So I kind of broke it up so that you could look at it as a single two-dimensional figure, and then as it's part of a larger three-dimensional figure. So all I would really need here is this distance. All right, so if I get the quote unquote height, the area of the base times the height, I'll be in pretty good shape. All right, so now I need some kind of method to make that determination. All right, so the tricky thing is when you get into 3 dimensions, it can be a process. All right, but you're also kind of looking at it from the perspective of, well, maybe I don't have to represent it with an actual height. Maybe I'm coming up with more of a general representation, right? So if I don't know the actual height of a figure, or I don't have the means to figure it out, I can just leave it as h. So I'm just going to call it, for now anyway, I'll call this h. I know the base area is 26.5. 26.5 times h would give me the cubic units that make up the volume of this figure. Right, so if I happen to know, for example, if the height h is equal to 5, then I could say 26.5 times 5. But the benefit of being able to do something like this in what we call general terms is to say, all right, well, what if it's 25 feet? What if it's 30 feet? What if it's 100 feet? I can always have a method by which I can come up with the volume. All right, so this would be a general rule for the volume of the figure. This would be an example of what we call a particular case. So 26.5 times 5, 132.5 cubic units. But if I needed to, on Desmos, for example, and other forms of technology, I could leave it as 26.5 times h and let h be some slider value. So let me just do a new blank graph. 26.5 times h, create a slider, and now I have the ability very quickly to come up with a volume if I wanted to extend my figure. If I wanted to make the room taller, like if I wanted to extend the roof on the house, like how much more volume would I capture? So if I had a height of 5, it would give me 132.5. But what if I wanted to double the height? Then I would be at 265. So now I have the means by which I can come up with the volume no matter what the height is. Right. So it's a more generalized approach to things. Let's see. Oh, okay. Yeah, question.
Professor, that 4.5 over there, does it mean something or just?
That 4 point, I honestly don't, I don't even know what that is. It really kind of tucked itself in there, didn't it? Honestly, that could be the height of this line segment, in which case instead of using 5, I would use 4.5. But I think I might have just accidentally put that in there.
Okay.
Yeah, that was a label from GeoGebra. I meant to delete that out of there. So just kind of pretend it's not there.
Okay.
So I'm going to go with it. Yeah, because like, for example, you remember that that cylinder problem that we did before. So if I wanted to, I could say pi r squared h in general terms, meaning only coefficients, no numerical values, and leave it kind of flexible so that depending on whatever the height is, I can come up with a new volume. Right? The one that I had on GeoGebra had what we call infinite volume, infinite height, which led to infinite volume. But if I wanted to cap it at 10 feet or 100 feet or maybe only 1 foot, I would have the flexibility to do that using something like Desmos or GeoGebra. Right. So in that problem, if I remember correctly, and I don't, okay, so this was a radius of 4 centimeters. So if I leave it with a variable h, that gives me the flexibility to manipulate the height and determine what all the different possible volumes are. So let's say in this case, I wanted to go up to, I'll call it 20. Then I would know that its volume would be 1005.0, right? So it's kind of a nifty way of being able to look at these things as not being just one and done problems. They're more flexible. But if it is 4.5, you can do that too. Because when I constructed this on GeoGebra, I needed to put in particular heights. So I just forgot to turn that label off. I'll take it as a typo, of course. Anytime you change something, it's a typo. And it's an opportunity for bonus. But let's say the height was 4.5. Then just going back to the general rule, we know that it's 26.5 times h. I could make my h 4.5 and get it to land on it, which it doesn't want to do, but so I'll just type it in. My volume would be 119.25 units cubed. So, yeah, and the benefit of being able to do something like this is like, you think about those multiple types of questions that you could be asked, and I'm not dropping any hints except I totally am. If I gave you an irregular shape and I said, find the volume if the height is 4.5, if the height is 5, if the height is 10, if the height is 20. This gives you a very quick way to come up with that. The base area, take that, find that number, put it in Desmos, multiplied by h. Oh my Lord, they just hit a home run. Okay, 4-0. So yeah, you would be able to come up, you crank out those answers very, very quickly. All right, so that's kind of the point. So like I said, we're gonna skip over the proofs. Well, I don't know if I said it, I alluded to it, I teased it, but they're not really the priority at this point. Right. So the next couple of pages are out. So that's the good news. You don't have to worry about proofs in this unit, which is kind of nice. It's more computational. But yeah, there's a lot going on here in terms of the computation stuff. So you gotta, kind of deal with that. But you don't have to worry about a proof. That's not a bad thing too. But we are going to move on to circles. But before we do that, I wanted to take a minute to talk to you about this week's assignment. All right. So I'm going to gloss right over this, get us lined up for circles. Again, it's I tweaked the packet, so if you had printed it up last week, you might not have these pages printed, but it's all on in the class note. Let me pause. Use the stopwatch on your phone It doesn't have to be an iPhone, but it should be some sort of smartphone, or at least, well, I suppose it doesn't even have to be a smartphone. It just has to be a phone that has a stopwatch on it. And find the number of seconds to the nearest hundredth to start and stop the clock with each hand. Right? So it's kind of weird, but I'll demonstrate real quick. So you go into the clock, you know, like I'm sure most people know how to use a stopwatch, but just in case you don't, you go into the clock, you go to stopwatch, you get the blank. So you see lap, or at least on this one, you got lap and start, right? So you're gonna do it with your non-dominant hand and your dominant hand, right? So what I'd like you to do is the non-dominant hand first, and then the dominant hand. All right, that's the way the data table is set up: non-dominant, then dominant. Right. So if you don't know what that means, if you're lefty, then you start off righty. If you're righty, you start off lefty. All right. So what you do is you hit start, stop, reset, start, stop, reset, start, stop, reset. Do that 5 times. So I'm up to, I think I did 3 times, 4 times, start, stop, reset, 5 times, start, stop, reset. And then the last time is the real data point. Start, stop, whatever that number is, minus 0.33, that's the number that goes into the table, right? Then you do the same thing with your other hand, right? So your dominant hand, start, stop, reset, right? So it's kind of hard to show, but yeah, you get the idea. Where, I think the camera. Start, stop, reset, but all with your non-dominant hand first, then your dominant hand, right? Only one finger, and you're holding it in your hand. So most likely that's your thumb, right? So, because what I don't want is somebody holding it with their non-dominant hand and then doing all the work with their dominant hand. That's going to screw up the data, right? So with one hand, just like it's easier to see when I do it with my left hand, start, stop, reset, start, stop, reset. The first 5 times are for you to get a little, you know, a little muscle memory going. And the 6th attempt is for you to get like a good sample value, right? And then you do it with the other hand. And, you know, like part of it is the placement of the buttons, you know, for a lefty versus for a righty, you know, like what's more convenient, what's more useful, you know? So, so that's what I'm looking into. That's the purpose of it. But it should be an easy way to get 3 points. Just, you know, just do your best with it. You know, it's beyond the scope of the course. So it's not like I'm not gonna give you a hard time if you screw it up. I just won't use your data, you know, but I'll still give you the bonus. You know,
Professor, after the 6th time, what do you want us to write down? What
whatever the time was for the 6th time.
Okay.
So you do it 5 times, you ignore those data values. On the 6th time, whatever that time was, that's what goes into the table.
Okay.
Right, so I got 0.33. So I'd go into book 2 here and click on the SharePoint thing, whatever. And then I put my name in there and I'd put 0.33. And then I'd do it again for whatever the next time was. All right. So that's the idea. All right. If you have any questions about that, we could talk about it after class, because I know it's kind of weird, and since it has absolutely nothing to do with the course, it's like, where did this come from? But you're helping me out, so I give you a little reward for it. It's kind of like the typo bonus. You know, you're helping me to improve my notes, so I give you bonus for it. You know, it's you scratch my back, I scratch. You know it. Not the drill. So anyway, that's something. And you know, between that, the word of the day, and all those bonus typo opportunities, I mean, let's see, 12. I mean, you get around, should be able to get around 20 bonus points for the course. I mean, it's not bad, not too shabby, as they say. Whoever they are. So, so yeah, you can do that. I'm going to go back to the notes now that I got everybody interested in doing something that has nothing to do with geometry. But we got 2 more short pages to go. And that would be it for the course.
Professor, quick question. Do we have an assessment next week?
So, yeah, we do.
Okay.
So it's going to be based off of essentially this one note set. And it's going to have the same structure as the last one. You know, the few short answer questions and then a couple of tasks to do. But there won't be a proof, right? So you won't have to do a proof this time. And then while we're talking about it, so next week is the 3rd unit assessment. I'm going to do my very best to get those graded and course grades posted as quickly as possible after you've taken those assessments, because as hopefully we all remember, there is the incentive that if you meet the attendance requirement, some of us are very aware of that, and some of us, maybe lost track of it. But if you meet the attendance requirement, you can drop a lowest assessment grade, right? And that, in most cases, hopefully means that you wouldn't have to take the final assessment, which is 2 weeks from now, right? So next class, the assessment could be it for you, right? So let's say, for example, and this is just kind of rehashing the first class of the year. Let's say, for example, you haven't missed any class, or maybe you only missed 1 class. You did well on all of your assessments, and you're living with a grade that you're happy with, right? So you have, let's say you're in the A range, and this is after next week's assessment. Then you have an A for the course, and you're done, right? Let's say you met the attendance requirement. You haven't missed, more than a class or 2, and you take the assessment next week, and you have, let's say, a low 80 average. So you're in the B range. Now you have a choice, right? And let's say you've done all the bonus, so you kind of maxed out on the points that you can get in other ways. You have a choice. If you're happy with the B, you could take the B and go. If you're not happy with the B, then you would take the final assessment, and that would replace the lowest score that you had previously earned on a unit assessment, right? So let's say you had just 1 unit assessment that was holding you down, 1 poor grade. That final assessment would swap that grade out. Now, if you're absent like 7 or 8 times already, then that's irrelevant because you don't meet the attendance requirement. But if you only have like 1 or 2 absences, and you haven't been late a bunch of times, then you're in good standing. This is something that you could be looking at some good news, right? I have graded I know it took a while, but I have graded the assignment 4s. So you definitely want to have a look at those. You also want to have a look at anything that you might owe me, right? Because I know some people are falling behind on the discussion. Some people owe me some old assignments. I'll still take them. You're going to lose credit, but I'll still take them. That'll help your grade. But you may have to take. You kind of look at the final assessment as overtime. You haven't gotten the grade that you want. You want another crack at it. That's what overtime is for, right? But if you're pulling a grade that you like after that 3rd assessment, there's no reason for you to take the final unless you want to improve your score. Question.
So, Professor, let's say all of that being said, on the final, and you're okay with an A or B range, do we let you know that we don't want to take it, or how would it work exactly? Do we not just do it? Let you know.
Well, as a courtesy, it would be nice, but
Okay.
you don't have to. I mean, if you don't show up, I assume that you're not going to take it.
Okay.
The only people I'm worried about in those instances would be the people who are carrying a failing grade and they don't show up for the final. And I'm like, why did you not show up for the final? You could have passed, So that's a different story. But yeah, as a courtesy, it's nice to know. But you know, since it's a remote class, I got to be on anyway.
Yeah.
You know, if it were an in-person class, I'd definitely like to know so that I would know how many exams to photocopy, how many assessments to photocopy. But this isn't really like that. So, you know, it would be nice to know, but it's not 100% necessary.
But just
That
log in.
being said, if you're not sure about your standing, like don't just guess. You know, reach out to me, send me an email and say, listen, I think I don't have to take the final assessment, but I'm not 100% sure. Can you confirm what my grade is? Just so I know. You know, and I'm happy to do that.
Thank
Would you rather like we send an email or like pop in the day of the final, just be like, hey, I'm not going to take it. See ya. Like what would you kind of prefer, I guess, to get that across to you?
I think the email is probably the best way to go.
Okay, gotcha.
Yeah, because I don't want to put people out. You know, like if you're not going to take the final, you know, like yeah, I think yeah, it's probably preferred that you would just shoot a quick email.
Gotcha.
Professor, all the extra points for like the words and things like that, were they already put onto our grades?
See, that's the great news. I've never successfully figured out how to incorporate bonus into the average on Blackboard.
Oh.
So the bonus credit shows up on Blackboard as a score, but it's not factored into your grade yet. So I have to go through and manually do that. So whatever your grade is now, if you've done bonus work, then you could expect it to be higher than what you see on Blackboard. Right? Especially if you're like right on the bubble. Like I know there's definitely a couple of people who have grades that are right on that borderline for an A. And it's like, I already know you have an A at the moment, and you still got to take the third assessment because you've got like 10 bonus points on it. You know, so that's another thing. But I always do that after the third assessment, just so I can make sure that the information is as current as possible. I mean, so that, you know, like it would be nice to have the information in real time, but this is the easiest way I could figure it out. Right? But again, if you're concerned about that, I can always, you know, it's tough to do it for an entire class, you know, at a moment's notice. But if you're really concerned, just send me an email and say, I'm just curious about what my average is currently with bonus included, and I'll tell you. All good questions, folks. Yeah, because you know, like I know it's a weird policy, but it's definitely as student friendly as I can make it. So that I always look at it like.
I was just saying it's actually a great policy.
Oh, thank you. But yeah, I never wanted to hold people back, you know, especially over like little things. So I mean, if you've been doing the right thing, you know, coming to class, doing what you're supposed to do, trying, you know, like there's always like good things will happen. It's just a matter of, you know, how we can make those good things. So, and if you're concerned about anything, just shoot me an email and we'll talk it out. We'll figure it out. Okay, so the grand finale, the last topic of the course, circle geometry. Right. It's not the last topic because it's the most complicated, right? Just in case you're wondering, right? That's always something that people are worried about. It's like it's the last topic. It must be the hardest thing ever. It's just different. In fact, this whole course has been going from one area of geometry to another area of geometry. You know, like it's just a different focus. Now it might seem more challenging, but it really is the same level of difficulty. Right? There's more terminology here, but you know, like we had a lot of terminology when we talked about logic. So you know, it all balances out. Right? Tangent to a circle, a straight line that touches the circle at one point is called the point of tangency. At the point of tangency, the tangent of the circle is perpendicular to the radius of the circle. Right? So perpendicular lines form right angles. right? So if I'm looking at this diagram over here, we have this A to B, this a pinkish looking figure, or well, it's a line, but I don't know why I call it a figure. Still a figure. Kind of wanted something sort of pink to go along with it. That would be the tangent line. Right. Now this, as we know from before, is the radius. This line segment. The line segment that is the radius and the tangent line will always intersect to form a right angle. Right. So we could always count on that being 90 degrees. So when you look at the first question, BA is tangent to circle C. All of these formatting issues that you see here, I know some people are looking for typo bonus. All of these formatting issues here, those are typos. Yeah, that can be fixed. And everyone counts as a unique one because like it's one thing to tell me that there's a typo on page whatever. I'll look on page whatever and only see one typo and only fix one typo. But if you tell me each one individually, then I stand better of a chance of fixing it all. Right. So what we learned is that the tangent and the radius are going to intersect to form a right angle. I can make a right angle. Right. So I know that's 90 degrees. We know that there's 180 degrees in a triangle. So if I knock off the 90 and knock off the 22, I'm going to get 68 degrees, and that's going to be the angle X, or the angle that is X degrees. All by just knowing that that one relationship exists. Tangent to a circle creates a 90-degree angle with the radius. And so computationally, it's pretty easy. Just knowing that fact that makes it challenging. I don't even know. It's just more like that's the only thing that makes things work. Right? Just like in number 2, the 90-degree angle here. So it's another 180 minus that 90-degree angle. Knock off the 90, knock off the 38, and we're at 52 degrees. All right, so that's my X. All right. But then number 3 can be a little kooky. All right. So you look at that and say, well, that's a quadrilateral. How does that work? Same way. All right. So we're looking at a 90-degree angle here. We're also looking at a 90-degree angle there. It's because we have 2 tangent lines. But again, if a tangent line intersects a radius, it creates a 90-degree angle. So we have to know that there are 360 degrees worth of angles in a quadrilateral. 360 minus the 130 that they gave us, minus a couple of 90s, will give us X. All right. So 360 minus 130 is 230, minus 90 is 140. Minus another 90 would be 50, if I'm not mistaken. Just double checking, 180, 280, yeah. All right. Now, number 4 seems like it has nothing to do with what we're talking about, but it has plenty to do. Because if you create a triangle that has a right angle in it, That makes it a right triangle, of course, but it also means that the Pythagorean theorem is in play. All right, so I need to figure out the value of x. In a circle, all radii are congruent. Right, so radii, plural of radius, every one of those radii, or every one of those radius values, is going to be equivalent. They're all going to have the same measure. Okay, so if one of them's 3, they're all 3. So this one's 3. So is this one. So I now know that if I'm talking about this right triangle here, that one right there, I'm going to just kind of pull that out and look at it. It's got a leg of 3 and a hypotenuse of 10 and an unknown leg of x. I'd apply my Pythagorean theorem, a squared plus b squared is equal to c squared. 3 squared plus x squared is equal to 10 squared. 9 plus x squared is equal to 100. And you know, if this sounds familiar, it's because it is. We did this almost the same exact problem before, at least a right triangle with the same dimensions. X squared is going to be equal to 91. And when I take the square root of both sides, I get x is equal to the square root of 91. So it's honestly, it's more right triangle stuff. You kind of look at it and say, well, there's a lot of right triangle information that comes up in geometry. You know, triangles are the basis of everything. And right triangles, every triangle can be decomposed into right triangles. So you could always use the right triangle in some capacity. So it's interesting that, you know, one of the simpler concepts ends up being one of the most important. So then, more terminology. We have a minor arc, less than 180 degrees and equal to the central angle. The central angle is formed with the vertex at the center of the circle, whereas the major arc is greater than 180 degrees. Okay. So you kind of look at it and say, well, you have 2 arcs that are made by an angle within a circle. The major is going to be the bigger, the minor is going to be the smaller. Okay. So that's generally how it plays out. So that's what these diagrams are telling us. So you look at the major arc here is huge as opposed to the minor, which is smaller. In every case, no matter where you put that line segment, it can create an angle. This is a straight angle, this chord. A chord is what we call a line segment that goes from one part of the circumference to another. Right? A secant, which we get to on the next page, is a line segment that originates outside of the circle that intersects the circle in 2 places. Right? That would be a secant. Right? But that, you know, like I said, I'll get to that in a minute, but just kind of move that off. An inscribed angle is an angle whose vertex is on the circumference of the circle. The central angle, I think, is the easiest one to define because it's an angle that's centrally located. The vertex is at the center. Right. So right? So that's how we know the difference between a central angle and an inscribed angle. Right. And so again, the secant intersects the circle at 2 points. So I'll draw a little diagram for that in a second. I'll draw it now, but just kind of chuck it down here. And this would be an example. All right, so just some terminology, really. All right. Now, the inscribed angle is always half the measure of the intercepted arc. All right. The measure of the angle formed by the tangent and the chord is half the measure of the intercepted arc. All right. So that one's kind of weird. But the intercepted arc, if you look at this diagram, you have your inscribed angle, which would be right here. This would be my intercepted arc right here. All right, those measures are proportional to one another. The inscribed angle has half the measure of the angular measure of the intercepted arc. Right, and that's because there's 360 degrees in a circle. So every little segment can be accounted for in a linear distance, but it could also be measured in terms of a degree of movement, right? So if I'm talking about a protractor, I can get this angle pretty easily, but I would want to know how that would relate if I were to project that angle out onto a circular surface, right? So what fraction of 360 degrees am I working with? As it turns out, if you know what your inscribed angle is, all you have to do is double it and you have your intercepted arc. Right. And then, you know, we have some other relationships that come into play down below, but we'll get to that in a minute. Right. So looking at the example 5 here, it doesn't really seem like we have enough information, but we do have actually 3 inscribed angles. Right, one at A, one at B, and one at C. But if I just focus on this one, I have this inscribed angle and then the corresponding arc. Right, so whatever this angle is here, double it, and I'd have this one. Now this is an equilateral triangle. And that's because all sides are congruent. In an equilateral triangle, all angles are congruent. If all the angles are congruent and all the angles add up to 180 degrees, then each angle must be 60 degrees, 1/3 of the total. So this must be a 60-degree angle. So X is going to be equal to 2 times 60 degrees. So 120 degrees. All right. Now, if you compare that, you know what I mentioned before is that there are 360 degrees in a circle, which means, you know, like if somebody does a 360, they're doing one full turn. So let's say I started off at B. So I start off right here and I do one full rotation around. Okay, that was unintentional. Don't connect, don't connect, don't connect. It connected. And try it one more time, but this time I'm not going to let it connect. Just going to look like crap. All right, that's 360 degrees. Right, what's happening here is just going from here to here, that movement would be 120 degrees. All right, so then you just have to ask yourself, you know, as a quick informal check, if I did that same 120 degree movement 2 more times, would I get to 360 degrees? Well, that would be if I did the movement here and then again here. It does appear that this little piece here is 1/3 of the entire circle. So we're in pretty good shape. Right? That's a good way of getting intuitive understanding of the relationship. Right? I'm still kind of desperate to make this diagram look halfway decent. All right, best I can do. All right, but then sometimes, you know, it doesn't seem like you have enough information. Oh, I think I led the last problem off with that same comment. Yeah, it doesn't seem like you have enough information, but you do, because if I look at this inscribed angle here, the intercept at R would have to be double that measure. So that gets you to 80 degrees over here. Right, so getting from C to B, they tell us is 200 degrees. Getting from B to A is another 80 degrees. I need to figure out the angle at X. Well, if I can only figure out the intercept at R, then I would be able to make that determination. So use this neon green here. So this figure here would be what I was looking for, right? So that intercepted arc, well, if we know it's got to add up to 360 degrees, 360 minus what we have, minus 200, gets me to 160, minus 80 gets me down to 80. So this has to be 80 degrees. X is going to be equal to 1/2 of 80. Because the inscribed angle is always half of the intercepted arc. Right? So X is going to be equal to 40 degrees. So the secant, again, it's a line that intersects a circle at 2 points. It's wonderful. There's more to that, but we only need to know, okay, there could be a line that originates outside of a circle and intersects the circle in 2 distinct locations, right? And the chords are line segments that intersect the circle, but are contained strictly inside of a circle. In fact, part of a secant is a chord. Right? The measure of an angle formed by 2 lines that intersect a circle is half the sum of the measures of the intercepted arcs. And I'll show you that in a sec. The measure of an angle formed by 2 lines that intersect outside of the circle is half the difference of the measures of the intercepted arcs. And then the last one involves products, which we'll get to in a second. Right? So let's just start off with, well, actually, these are kind of out of order. So let's do the second one first. So this relationship, the measure of an angle formed by lines that intersect outside of a circle is half the difference of the intercepted arcs. So this would correspond with number 7. And so I'll just draw a little arrow here. So if I wanted to figure out any of these arcs, if I know the angle on the outside, I could do that pretty easily, right? So W minus 110, well, whatever that difference is, cut in half, I'll put a 1/2 in front of that, is going to be equal to a 70 degrees. All right. So if I wanted to figure out W, I could do it with trial and error, or I can double both sides, and get W minus 110 is equal to 140. And then just add 110 to both sides. W degrees would be equal to 250 degrees. Right. That being said, yeah, for this question, you wouldn't really have needed to do any of that, only because you know there's 360 degrees in the circle, and they're telling you this part is 110, so the other part has to be 250. Right? I just did it this way to show you the relationship, but you know, like if you're doing this on your own, do it the easiest way possible. Right. So this is a general representation for this. I'll just draw a little diagram here. Kind of like a little snow cone sort of deal. So if I call this A and I call this B, and put the B in the middle, and I call this C, then what I'm saying here is that 1/2 of A minus B is equal to C. That's all that relationship is really talking about. Right. So number 10 is like that also. Oh, actually, I'm sorry. Number 10 is the first one. Going cross-eyed there for a second. So for that one, I'll come back to 8 and 9 in a second because those have line segments involved in them. So, yeah, for this one, the measure of an angle formed by two lines that intersect a circle is half the sum of the measures of the intercepted arcs. All right. So two lines that intersect a circle. That's what's happening here. Let me draw a little arrow jamming here. It's going to be half the sum of the intercepted arcs. So in this case, x degrees is going to be equal to 1/2 of 20 plus 90. So that's 1/2 of 110, which is 55 degrees. All right. So more general form for that, like I did for the last one. I'll just draw a little teensy tiny diagram, which should have been in the original notes. So we'll call it a typo. Typo. That took a walk on me. Come on, lock in. Okay. So I'll bring it in and then I'll bring it out. So we have these little pieces here, this one here, and this one here. And then we have this little angle in here. So we'll do the same deal. We'll call it A, B, and C. So the relationship is that A is equal to 1/2 of B plus C. So it's really the average of the two arcs. All right. And then the last one would be this green. I'll do for a given point in a circle, the product of the lengths of the two segments from the point to a circle is constant along any line through the point in the circle. All right. That's probably the most complicatedly phrased one, but it's probably the easiest one to compute. Right. So for a given point in a circle, the product of the lengths of the two segments from the point to the circle is constant along any line through the point in the circle. Right. So it's talking about a proportional relationship. So this would be consistent with number 9. So each one of these line segments is broken up into pieces based off the intersection. Right? So what this is telling us is that if we take the 8 and multiply it by the 2.5 and set that equal to the x multiplied by the 2, we'll be able to solve for the x. Okay. So 8 times 2.5 is 20. You get 2x. So x is going to be equal to 10. All right. So the little diagram for that one. Basically like an x inside the figure. It doesn't have to necessarily go through the center. I'll just kind of do it a little bit askew here. Bring it in. We have A, make it a little thinner. A, B, we call this C, D. So what this is telling me is that A times B is equal to C times D. And so that's a generalization of what we just did. For whatever reason, and I don't want to make things any more complicated than it needs to be, it's getting late. I don't have the rules written down for the remaining examples. So that's, I guess, your game, my loss. So we'll just toss 8, 11, and 12. They're good examples, but it's like another page of notes to talk about those. So I don't know what I was thinking. I must have deleted it, but yeah, this page didn't really come out the way I wanted it, obviously. All right. So yeah, a lot of typos for somebody, for multiple people. I don't believe I gave the second word of the day yet, which would be opportunity. Opportunity is the second word of the day. Right, so it seems to be the general theme of the second half of this lesson. So that's a good thing. So yeah, actually, honestly, I think should be like a word of the day at some point, because I keep saying that one too.
What was it again? Sorry.
Opportunity.
Okay.
Opportunity is the word of the day. Second word of the day. So, and I did it again. That's where we're going to leave it. So the ones that we crossed out, you wouldn't be responsible for. You don't have to worry about that in terms of content. And yeah, so like I said, next class, you want to have completed the assignment 5. Next class is the third unit assessment, same structure as the previous ones. A few short answer questions followed by a couple of tasks, right? But no proofs, as I mentioned before. And then we already talked about the final assessment. But I'll put that in writing as we go forward. I like to send out an announcement related to that kind of stuff. So just be on the lookout for that. Right. So like I said, that's where we're going to leave it. If you have any questions, stick around. Otherwise, enjoy the remainder of the evening. And I will see you all next week. And if you came in late,
Professor,